In the previous video, I talked about two models that are used in theory, real RAM, and especially we're going to use real RAM in computational geometry. These models have some advantages. In particular, they make life very easy for theoreticians, but they're too simple and too unrealistic, so they create a gap between theory and practice. To show an example of a model that tries to narrow the gap, I will need to tell you a story. So this is an example. I borrowed this from lecture notes of Rolf Fagerberg in DTU. So the story starts by assuming that you're working for a computers company and you want to implement sorting algorithms. Okay, so you look at your, you remember your courses in the past and you realize that you know three sorting algorithms: heap sort, merge sort, and quick sort. And you need to figure out which one you want to implement. You look up their running times and you realize that they're all running in log n time, and you look up their constants and realize that they have all the small constants, and you look at their implementation and you realize that they're all relatively simple to implement, and the basic operations, the number of basic operations for all of them look more or less the same. Okay, but then you'll notice that there are some other ways to distinguish between these algorithms. In particular, you read that quicksort it's a randomized algorithm, so it needs random numbers, and it's not worst case optimal. In the worst case, you could run in n squared time, so it's only n log n in the expected case or in the average case. Merge sort needs extra space to do the merging, so in general, to merge two arrays, you need an extra space. So to sort n numbers, you actually need 2 times n space to do the sorting, whereas quick sort and heap sort don't need that. They can be in place, so you don't need any extra space other than the array itself to do the sorting. So in other words, once you categorize these advantages and disadvantages, you realize that heap sort is actually beat all of them. It is worst case optimal and it's in place, so you don't need extra space to do it. So you're happy, you implement the solution, and then later you're bored and you want to decide all three algorithms and compare them. So you do that. You implement all of them. You run your algorithms on very large input, and you divide the running time by n log n. Since the algorithms are analyzed or expected to be n log n in running time, if you divide the running time by n log n, you should see a constant. And I guess you could expect some algorithm will have slightly higher constants and whatnot. But what you see is quite surprising. This is the result what you see. So merge sort and quick sort are relatively stable algorithms. It means that if you divide the running time by n log n, you see a constant. And you also see that quick sort has slightly lower constant than merge sort. But heap sort kind of starts low and then blows up a little bit, then blows up a bit more. And you cannot explain this behavior. There is now a gap between theory and practice. Theory does not predict heap sort to have such a behavior. And the blow up in the constant is actually quite significant here, right? So this is more or less close to, let's say 4 to 5 constant or constant factor blow up. Okay. How do you explain this? You can explain this by noticing the following phenomena: that once you take the size of your array and you match them with the size of various memories that you have in your modern computer, let's say L2 cache, L3 cache on your RAM, then you'll see that this behavior makes sense. We're not going to go into the details of this, but the short version of the story is that the standard model that I introduced earlier, that had only a CPU and the memory, that you could access any location of the memory for free, that's not true. A modern computer looks more like this: that you have a CPU. The CPU has a bunch of registers that can be accessed in one clock cycle by the CPU, so that's super fast. The CPU also has a level 1 cache that is quite fast, but its access time is a constant factor larger than the access time of register. So let's say it takes 5 times longer to access cache 1. It takes quite a large number to access cache 2. Accessing RAM could take up to 100 cycles, so it could be 100 times slower than accessing a register. Accessing a hard disk is much slower. So in other words, if you want to access an element that is in the memory, it depends where the element is. Is it in the RAM, cache 2, cache 1, or register? Or maybe it's even on the disk. Theory cannot do this. When theory considers only 2 levels of memory, a CPU, or only 1 level of memory, a CPU and RAM, all these complexities go away, so they are not reflected in what we do. So we're going to look at one model that tries to be a bit closer to reality, and the model we're going to look at considers two levels of memory. So you can apply it to a CPU and two memories. So you have a fast memory and you have a slow memory, and that is known as the IO model. The IO model can be applied to any two levels in the hierarchy. So for example, you could apply with respect to cache 2 and your RAM, then the cache 2 will be your fast memory, your RAM will be the slow memory. In general, this model can be applied to any two levels. So in other words, it considers the notion that there is a fast memory and then there is a slow memory. And then we can try to see how we can analyze algorithms in this model. So that's